Peter Rosenbusch.
Thank you very much, Jean-Marie and Emanuela, for the introduction, and thank you very much for inviting me to present our work here and for listening. So, I have to stand here. Yeah, you can't see the picture yet. I will talk about the work I did at the Observatoire de Paris, which is the logo here. And this work I did in a team of several researchers. Four of them you can see on the picture here. I also wrote down their names here because this is not work I did on my own. This is important to say. The whole activity was started by André Clairon. Oh, I'm sorry, I got the letter wrong. André Clairon, who unfortunately passed away 3.5 years ago. But he really founded this activity, which I'm going to talk about, in the 1980s. So it takes a long time to make a good clock. I also want this talk not actually to be a talk, but more a lesson. I want you to learn something. I want you to take the fascination away, which we have in looking at nature, in trying to understand nature. I want you to be as fascinated as we are from our work. So it's important that you participate in this lesson. Since we're in an old school, I think it's quite appropriate that it's a lesson. And I also want you to ask questions, because only when you ask questions you start to think about what is actually going on and how to proceed in the next step in your thoughts. So the subject of my talk is what is time? What is time, or what is the time? And from there it's quite easy to get to the agenda. The first question is what is time, and the second question is what is the time, as in who tells us what time it is, whether you arrived in time to this conference or not. So I start with time, which is the more difficult part to me because it's kind of philosophical, and this is not really my craft. And to address this question, I started the other way around. This is also a very common way of working. If you don't know the answer, you ask the opposite question. You try to exclude the answers. So let's think about moments where I don't want to know the time, where I want to forget time. One is you climb a mountain, you arrive at the top after all the effort, and you see the magnificent sunrise or sunset, and you just want to admire the beauty of nature. Another moment could be when you're with your beloved one on a beach, again admiring sunset or the nice weather. Also, which we had occasion to, and we still have occasion to admire or adore the Lord present among us. This is a moment when I want to forget time. Okay, let's put the question the other way around again. What's the moment when I need to know time? There's no choice. I have to have a watch or a clock. Let's say if I want to meet a friend, I have to arrange a time to meet. Or if I want to travel on a train here, you all know the clocks in the station, they are very important, so I won't miss my train. Another thing which in my recent work is important, to make a phone call to a colleague which is probably maybe at a different site, and I have to arrange a moment when we speak on the phone so that we're both present. And in preparing this, I realized in the morning I often hurry up and I make my children hurry up. We have to go to school. We're late. Look on your watch. And then I realized every time I look at my watch, it's actually to meet someone. If I take the train or if I go to school, I will meet someone. So rather than being stressed about being late, let's think it the other way around. It's nice. I will go to meet my teacher, my colleagues I don't know who. I'm sorry, I have to drink because my voice easily goes away. So let's go back to the two friends who want to meet. How can we make sure that they meet in time? Let's say they agree we will meet at 9 a.m. tomorrow morning. Then I thought about a prehistoric person who didn't have a watch or a smartphone to look at time. How would they say, let's meet tomorrow morning at 8 o'clock or 9 o'clock? So you can have a couple of choices. One is, let's meet at sunrise, which is a good way because the sun rises every day, and so you know tomorrow morning 9 o'clock is about sunrise. The other one is, let's meet after 5,000 heartbeats. You have the heart in your breast, and it beats, so you can just count the heartbeats. So the first thing you have to learn is that time is a convention. These two friends have to agree on how they will measure time, how they will define the moment when they will meet, either by the sun or by their heartbeats. So the left choice, the sun, is they choose a master clock, one clock, which is known by both. Another example for a master clock is this. It's the speaking clock. So you have a lady which has earphones, I don't know whether you can see them, and you can call this lady, and the lady will tell you what the clock reads. So in this way, everyone in one country can call this number and knows the same time. So this clock is the master clock to everyone in this country. And this is how timekeeping started at the Observatoire de Paris. They had clocks, very good clock, which was the master clock for France. And anyone could call to the Observatoire and ask what time it is. In the beginning, there wasn't such a lady, so the director of the Observatoire had to pick up the phone. There was only one phone line, of course. He picked up the phone and he would tell you what time it is. And then he kind of got annoyed by the number of calls. And he invented a machine which would actually replace the lady. So the other choice is to take your heartbeats, which is essentially make two individual clocks, but these two clocks have to be identical. So that's the difficult part. If you take the heartbeat of these two friends, maybe they meet in the white person's house, so he will just sit in his armchair and wait. The heart beats at 60 beats per minute, very relaxed. The other guy is going there, and he realizes he's late, so he starts to run, so his heart starts to beat even faster, so he will be even later. So that's obviously not a good choice to choose the heartbeat as a clock, okay? So the rest of my talk will be how you make identical clocks. Let's start with an experiment. I'm an experimental physicist, so we do experiments to understand things. I want to make an experiment with you which realizes this kind of clock, where you have a large pendulum at the bottom and it swings from the left and to the right. You all know this, okay? So I need two volunteers, preferably not with earphones because you need to use your hands. Please, one person, fine. Need a second person. Okay, come up on stage, please, so everyone can see you. All right, you stand back to back, please, on the side. Back to back. Yeah, very good. No, so that people can see you this way. Perfect. And don't fall off the stage. Okay, this is for you. Now I want you to swing the pendulum. I will you do it along this way. Yeah. Put the finger in the loop. So I will give definite position, and let them go, and then you make them swing, okay? And you observe. Okay, thank you. You can stop. So, what did you... Hang on. We're not finished yet. So, what did you observe? One is faster. Okay. At least they are different, okay? Good, that's right. Now, this is because I cheated on Edouard, and you should take it here. So we'll do this thing again. You ready? It's better? Okay, good. So why it's better? Thank you. Thank you very much. So I will summarize what you just observed. Where's my pointer? So we have two pendula, one with a long string and one with a short string. This was the first experiment. They swing left and right. I start them in the same position. They swing to the right, back to the left, and back to the right, and so on. And then you realize, even though they start together, at some point they are no longer together and they may be even opposite, which obviously we don't want if we want to make identical clocks. So the second experiment was with pendula where the string has the same length, as good as I could make it, and you start together and they oscillate for a long time together, okay, and we are happy. So in comparing these oscillations, you can tell whether the clocks are identical or not. That's the crucial point here. This you have to take away. We need to look at these oscillations. We need to look at them for a long time because in the beginning, obviously, in both cases they were together. So we have to let them swing for a long time, and then we can tell whether they are the same or not. So some examples of good clocks which weren't made by myself. So this is another pendulum clock here. You see the weight at the bottom, but you also see that what I used as a string are several bars here. So this is a zoom, and you can just about guess that the bars have different color. So outside is kind of silverish, then more golden or bronze, silver, bronze, and so on. This is to keep the length of the pendulum always the same. Because if you have a metal bar, and the temperature changes, if it gets hotter, the bar gets longer. So the length of this pendulum will change if it gets hotter. Now, by using two different methods, which is steel and bronze here, in a special arrangement, you can compensate for the one getting longer because they get longer differently. And even you have a small hand here, which tells you whether you're still right or whether it's slightly off. Basically, it tells you what the temperature says. So this is one way of making a clock even better than what we've seen with the string. This is from 1780. Now, in the early 20th century, we got quartz watches. You probably have, well, I don't know whether you have one, but at least you have the same thing in your smartphone. And what you really have in your smartphone is on this picture. So quartz can be a very pretty crystal, and you see some of this crystal is transparent here. So what they did here, this is about 2 or 3 millimeters long. You can about guess the fingers here. They cut from this crystal a tuning fork. So a tuning fork is this one, which I borrowed from Père Denis. It makes a sound. Okay? So it has the two arms oscillating against each other. It does this all the time. Okay? And the same tuning fork you have here, you see the transparent crystal cut here into the form of the tuning fork. This this is when my voice goes away. And on the tuning fork, you have these gray strips, which are electrodes, so you can send the signal in, make it oscillate, and also detect the oscillation. So it's physically a tuning fork in your clock, in your watch, which makes the time. The third part is an atom, and now I come to atomic clocks. So atomic clocks, the first one was realized in 1949. Do you have a question up to here? Because now I'm going to change. No? That's a bad sign.
You're a good teacher.
Okay. So atoms, you may know what they look like. You have electrons, which are negatively charged, protons, which are positively charged, and neutrons. So protons and neutrons, they are in the nucleus. This is the favorite region of Père Jean-Marie. And the electrons, they evolve around. So the nucleus is very dense and very small. We forget about it, what it really looks like. It's just that it's positively charged. And the electrons, they go around in specific orbits. So I work on the electrons. Père Jean-Marie, he worked on the nucleus. Because the electrons are negatively charged and the protons are positively charged, there's an attractive force between them. This you all remember from very old lessons, I suppose. So we can imagine there's some kind of spring between these two, which attracts the electrons towards the protons. Now I've brought another pendulum, which uses a spring, and it goes up and down. Okay? But it has this nice spring, so I don't need to swing it left and right. It also goes up and down. There are two particular positions in this pendulum. One is when the puppet all the way up, and when it's all the way down. Okay? So I just give names to these two positions, which I name E1 for the down and E2 for the up. In the same way, I can give names to the position of the electron in the atom. So this outer orbit I will name E2, and the inner orbit I will name E1. Okay? Now what really happens is that the atom, or the electron in the atom oscillates between these two stages, E1 and E2, in the same way as the puppet goes up and down. It oscillates between E1 and E2. And the frequency of this oscillation, this is the clock frequency. This is what gives us time. The electron oscillating between these two orbits. And as I'm a physicist, I have to show at least one formula in my talk, and this is it. So this is the formula. The difference in energy between the state E2 and E1 is the clock frequency. There's a constant here, h, which is the Planck constant. So Max Planck was a physicist at the turning of the 19th to the 20th century, a German physicist. And he invented quantum physics, which now is in everyone's mouth, which is very fashionable. And he had this constant named after him. Sorry, my voice is really losing. So, the convention of the time, this is what we all agreed on, and which you have to follow if you want to stay in time with the rest of us, is written down here. It's a kind of book kept by the BIPM, Bureau International de Poids et Mesures. It's an international organism which is just outside Paris. And they regroup researchers and people like me from all over the world. Together we think about what's a good way, and we all agree on this is the way how we should define time. The SI unit, SI is System International, so it's just a name for all the principal units. Unit of time is the second, which is is already good to say it's a second. It's not 1 hour or 1 month or 1 minute. So we all know what we talk about. The second is the duration of a bit more than 9 billion periods of the radiation corresponding to the transition between two fine levels of the ground state of cesium-132. So that's just the short version, okay? But it's not complicated, you know it already. It's the transition between two levels of the cesium atom, okay? The two levels I've shown you here, E1 and E2, it's the transition between the two. In here it's written in 9 billion periods, so 9 billion oscillations back and forth between these two. Once you've counted 9 billion, you got to 1 second, okay? The difference between your counting heartbeats and counting this atom is that this atom doesn't depend on how fast you run. So, and it's cesium-132. Cesium is shown here. It's a metal. It looks shiny like silver. It is chemically very similar to sodium, which you all know from sodium chloride, which is stable salt. So we eat this every day. But when it's on its own, it's very reactive. Like sodium, it reacts very strongly with water or with air. So we have to keep it in a glass ampule, which you can see here, so it doesn't react with air. So my job was to put this nice writing by the BNPM into practice, because when you've written it down on paper, you can't make a clock from it yet. It's like money. You can't eat money. It's a piece of paper. So all our work is putting exactly this writing into practice and give a physical signal, a real clock where you can read the hands go round. And the clock looks like this. So my clock was called FO1. It fills a whole laboratory, 1 room about. Sorry. You have lots of cables. Well, here you see only a few ones, and there were really more. You have electronics. You have here optics. So all these black bits, they are holders for lenses and mirrors, because there's light going around, and you need the light to prepare the atoms for the clock measurement. Then you have this steel can, and inside the steel can, which you can't see very well, is a tube. So we evacuate the tube, we pump all the air out of the tube, because the cesium reacts with air, as I said, so that inside the tube there's only the cesium. This steel can is to shield from the magnetic field, so that, for example, the Earth's magnetic field doesn't interfere with the atoms, because the transition, although we chose our atom well, still depends on the magnetic field. Okay, so now you have an impression what it looks like. Now I come back to the question, how good is my clock, or did I really build identical clocks? To tell how good is your clock, you have to build at least another one, compare the two, and see whether you get the same oscillation as we did with the pendula. The better is even you build 3, because if the result doesn't agree, you don't know which one of the two is wrong. So at Observatoire de Paris, we built 2 clocks, FO1 you know already. This is a picture seen from the sky of Observatoire de Paris. This is the main building. This is the garden, the nice garden. My clock was in this building, and then we had a second clock, FO2, which was run by my colleague Jocelyne, which was situated in this more modern building, and this is where Father John Marie studied. Yeah. So we compared these 2 clocks, and unfortunately we realized, although they started together, they're no longer together after some times, like the 2 pendula, which didn't have the same length. That's, then we're not very happy, and we have to think, what's wrong? That's what we do most of the time, think what's wrong. The question is, are the 2 clocks really identical? And we've went through a number of things, a number of lists, and they don't explain the difference. And then we realized, well, one clock is in this building, which is on the ground floor, street level. And the other clock of Jocelyn, is in a different building, but it's in a basement. So you have to go down a couple of steps to get this clock, and the height difference is actually 4 meters. So has this a role? Is this important? Well, in the beginning we don't know. So we go to the books, we read literature, and we get to a man named Albert Einstein, who predicted the theory of general relativity, which you may have heard, and it makes, well, it's kind of scary, but it's not so dangerous. So Albert Einstein predicted that near massive objects, which is in this case the Earth, because we're on the Earth, clocks tick more slowly. And the difference is 10 to the minus 16 per meter. So don't try to understand what is 10 to the minus 16, I'll tell you in a minute. But it's important you have this variation per meter. So our clocks being at a difference in distance to the center of the Earth of 4 meters, the difference is 4 times 10 to the minus 16, and yes, it agrees with what we measured. So we understood why the two clocks were different. And now as we understood why they were different, we can just subtract this difference, and then they are really the same. And this is what we do with a number of effects, temperature, magnetic field. I want to show you a picture from my colleagues in the US, from NIST, which is National Institute of Standards, so they are the equivalent of Observatoire de Paris for the US. They make the time for the US. And there's a student who made a very nice experiment to show, again, the theory predicted by Albert Einstein. So the student is sitting here. This is his clock, which looks kind of similar. So you have this black thing is the side of the table, the optical table. On the table you have lots of components, black and shiny cables. It looks very much the same as my clock. The big metal can is smaller here because they're using a different atom. But it's a different detail. So he compared this clock to a second clock in their lab, which I don't show. He made the first measurement in this state, which are these data points, and then he lifted the whole table up. He just put a lab jack, lifted the table up, put some more blocks, so the whole table was 30 centimeters higher. He compared his clock again to the other clock, which hadn't changed, and he got these values here. And you see there is a clear difference between the two. So just lifting your clock up 30 centimeters changes the frequency of your clock in a way which you can notice. Okay? This was predicted by Albert Einstein, and we use it every day. It's not something in the stars at the end of the universe. It's here in the lab every day. So now I come to the numbers to explain what is 10 to the minus 16. I made a kind of table. I told you about FO1 and FO2. They use cesium as an atom. The accuracy of the clock is 10 to the minus 16. Einstein's theory predicts 10 to the minus 16 per meter. So we need to know the position of the clocks with an accuracy of 1 meter so that we can get to this overall accuracy of the clock. Okay? Now the new clocks which are being built right now, and you saw the one in the US, they use different atoms like strontium, deuterium, mercury, or there are a number of candidates. And they're even better. So they get to an accuracy of 10 to the minus 18, which is 100 times better than 10 to the minus 16. The theory of Albert Einstein is the same. It doesn't depend on the atom. So they need to know the position of the atoms with respect to the center of the Earth with an accuracy of 1 centimeter. Well, you look kind of lost. So I put my atoms here, and I need to know the distance to the center of the Earth with 1 centimeter accuracy. The diameter of the Earth is something like, I don't remember, 2,000 kilometers. The circumference is 4,000, so it's 40,000, it's 8,000. So 8,000 kilometers with 1 centimeter precision. The real feeling for numbers is you get from this 10 to the minus 18. 10 to the minus 18 is 1 second in the age of the universe. So if these clocks at NIST had existed at the Big Bang, they would be off by 1 second today. You're falling asleep. This is the point of my talk. If the clock had existed at the Big Bang, at the beginning of the universe, they would be off by 1 second today. Okay. Wow. So, but this is actually a real problem, the 1 centimeter. You can imagine that you can't know the position of the atoms with 1 centimeter accuracy. So we're starting to turn the problem around. We're not using clocks anymore to measure time, but to measure position. As I showed you, you have 2 clocks. One you leave fixed, the other one you lift up, and you know you lifted it up by 30 centimeters. So in doing this very well, you can start to measure differences in height, say in Europe and in the US, which are really difficult to measure otherwise. So clocks in future will measure position, not time. Well, time as well, but also position. Okay, I come to a summary. Time is a convention. It's a book kept by the BRPM. Time is defined by the energy difference in the cesium atom. And new clocks use other atoms which reach 10 to the minus 18 accuracy. Okay, this is about half of my talk. Do you want to hear the second half, or shall I start? Right. Now the big question people always ask me, is it useful? Okay? So, well, I told you already it's useful to measure position, but are atomic clocks useful for other things? Has anyone seen this picture? No. Yeah, one person has seen this. Okay. Okay, who can tell me what it is? Yes, you were the... Yes, very good. First, the first ever picture, direct picture of a black hole. So you see a ring of light, and in the center is dark. Oh, the picture is not very bad. The center is dark because there's a black hole, so the light can't escape from the black hole. It can't come to us. There were other observations of black holes, but they didn't show the actual hole, so they're more indirect observations. So it's a black hole which was discovered at the center of the galaxy Messier 87. It's at 2,000th of the size of the you're familiar with big numbers now, no? It's at 2,000th of the size of the universe from us, which is 55 million light years, so that's not all that far. It was observed during 2017 by a collaboration of many telescopes on Earth. I will come to this. And it was published in April this year, so very recently. And this was only possible because there were good atomic clocks, and this I want to explain to you. It's kind of lengthy as before, but I think we get through it. So we do another experiment. It's always good to start with an experiment. Can you all see the piece of paper? Who can see the piece of paper? Yes. Wow, that's only half of you. Let's try this again. Who can see the piece of paper? Yes. Oh, that's better. Okay. Who can see there's something on the piece of paper? Yes. That's very good as well. So now I want to do the experiment sincerely. So you don't tell me what you think you see. You tell me what you really see. Okay? And if you're not sure, you don't tell me. That's important. we're doing science here, we're not inventing things. We don't do metaphysics. So, who thinks, who sees this thing like the top? A ring with a blurry white spot in the center. Hands up. No one? One. Oh, damn. Okay, who sees this as a black disk? No. One person. And who sees it? Yeah. So I drew too well, sorry. I wanted you to see it like the top image, okay? I explain you now why. Next time, I draw smaller. So, this is supposed to be our eye. No? You have a lens at the pupil, a lens in front of your eye, which makes a picture of things we see on the retina. And the way we see things depends on the size of the lens. Because the size of the lens, the diameter of the lens is limited, if we look at very distant objects, they become blurry, like in this case, up here. If the diameter of the lens was even smaller, then we wouldn't see the hole in the center at all. It would be a black disk. And if you have very big eyes, then you can see it clearly as a ring, and obviously you have very big eyes. Okay, so the bigger the diameter of the lens, the better you can resolve distant objects. Now I come to radio telescopes, which are almost like any other telescope. It's just they use radio waves. They look like this, which is a big parabolic dish. You may have one on your house, or you've seen it on other houses for receiving satellite television. It's the same principle. You have this parabolic dish, which reflects the incoming signal into this antenna, and there it's transformed into an electric signal. In this case, the radio wave is emitted by the black hole. This is supposed to be the black hole, and it comes to the antenna. It's also very much the same like Wi-Fi or your cell phone. In your house, you have an emitter of Wi-Fi, same kind of waves traveling to your portable device, to your smartphone or to your tablet or your computer. It's the same kind of radiation we're looking at. So, I told you already, so the wave comes in, gets onto the dish, onto the parabolic dish, and then it's reflected actually to the center, which I haven't drawn, and it's the antenna here at the very center, which transforms into an electric signal. As we have an incoming oscillating wave, the output signal is also oscillating. Then I drew these fine lines, which actually define planes of where the oscillation is maximum, okay? So this is, if the wave comes from a spot, it goes out like a sphere, and I can define these spheres or these planes where the maximum of the wave would be. Now, the important bit is the orientation of the dish with respect to these waves coming from the black hole, from the object. If the antenna is completely parallel, as in this case with these planes of the wave, then, and I say I pick a part of the signal which comes from the top and a part of the signal which comes from the bottom, as the two are at the same distance from the dish, the signals here are exactly the same. They oscillate with the same frequency because they come from the same black hole, but also because the waves are parallel to the dish. They start in the same way and they go oscillate together, and the two signals add, making one big signal at the output. Okay. Now, if the dish is inclined with respect to the object I'm looking at, the black hole, then you still have these planes, but at the top there's a bigger distance between the plane and the dish, and at the bottom it's shorter. So the top signal has the same oscillation frequency, but it starts oscillating up, and at the bottom it oscillates down. So these two are exactly opposite. And when you add the two, the result is almost zero, because one is going this way, the other one is going that way, and they add to zero. So this sensitivity between big signal and small signal allows you to align the dish in the direction of your black hole, or it also allows you to resolve, let's say, the top and the bottom of the black hole. This is what makes the image. As a physicist, we always try to make things simpler or cheaper, especially, because we don't have much money. So there's a small trick we can play. Rather than having one big telescope, we have an array, or say 2 telescopes or an array, but the principle is the same. If I put a small telescope here at the top and a small one here at the bottom, if they are aligned such that the wave comes in at the same distance for the top at the bottom, we have the 2 signals. The 2 signals are the same. The sum is a big signal. If the axis between the 2 telescopes is misaligned, so the distance is bigger here and the distance is smaller there, then the signals are the same, but they start in the opposite direction. So this one goes up and this one goes down. They subtract and the output is small. So I'm still sensitive to the orientation of my telescopes. I can still resolve the picture, but I don't need to build a huge dish like this. But this is an important trick which makes things cheaper. Now I come back to the drawing on my piece of paper, which you saw too well. As for the length of the eye, the distance between the 2 telescopes is important. So let's say in this configuration I would see my black hole just as one dish without the hole in the center. But if I make the distance between the 2 telescopes bigger, that's like increasing the size of our eyes. I can better resolve the ring, okay? It's the same principle. Now, how far can we make the 2 dishes apart? What do you think? What's the furthest we can make them apart? Like my arms? No. Come on, you're asleep again. What's the biggest distance I can imagine between 2 telescopes, between 2 objects? That's it. 2 on the different sides of the Earth. I put one on the North Pole and the other one on the South Pole. That's the biggest distance I can realize reasonably. I can send them into space, but that's expensive again. So this is what people actually did. We're all happy to have this good idea. And then we realize, well, we can't actually pull a cable from the North Pole to the South Pole. Damn. So we have to start thinking again, what can we do to pull a cable from the South Pole to the North Pole? No, we don't actually pull a cable. We use atomic clocks. So this is where the atomic clocks come in. This is what is the application. You have an atomic clock at the 1 telescope and an atomic clock at the 2nd telescope. And since the 2 atomic clocks are identical, you can use them to measure the signals coming out of the telescopes. So I explain to you how you measure the signal, which is a bit lengthy as well, but I think we get through it. At the top is the signal from the clock, which is typically faster than the signal from the telescope, okay? This is the signal from the clock. And every time the clock signal, say, makes a minimum here, I look at the signal from the telescope and I write down the value the signal from the telescope has. So at this moment, it's almost 0, I write down 0. Then next time, it's almost maximum, so I write down 9, say. Next time, it's halfway through, I write 7. Then it goes negative, I write 2, minus 10, minus 5, then it goes positive again, 2, 10, and so on, okay? So I have transformed this physical signal coming out of the cable of the telescope into a series of numbers, into something I can write down on paper. I do this at the top, and I do this at the bottom, and I got obviously different series of numbers because the two signals are different. I store these series of numbers on a USB stick, or a very big USB stick, or many hard disks actually. So it's a huge amount of data, but I can store it and treat it later. I don't need to do it immediately. I take the two hard disks, bring them to one computer, which also takes time as you go from the North Pole to somewhere, say, near the equator and from the South Pole, which actually in this measure was also an important part. The computer combines the two number series and calculates the signal which we would otherwise have had out of the cable, okay? So in this way, we can use distant telescopes thanks to atomic clocks. Yeah. That's, well, it's the same thing. Computer combines the two signals, and the whole generates this picture, which you all know, and the whole observation works only because you had atomic clocks on each side, and they were identical. Yes? So you don't only get one series of numbers as I've drawn it. The telescope is like a camera, a CCD camera. So in a CCD camera you have many detectors in an area, like a checkerboard. And the telescope is the same. So it has this kind of arrangement of detectors, and you get a number series for each detector. So you make the calculation for each detector. You get bright or dark for each detector, and then putting in a square board again, you get the image. Okay. This is my next slide. Sorry. Sorry. C'était en français. Okay. Damn. Oh, shit. So the question was, first of all, the Earth spins. So if you exactly on the North Pole and exactly on the South Pole, then your telescopes don't move. But as Vincent said rightly, the axis of rotation of the Earth is not stable. It also moves like this slightly. So the question is, how can you know where the telescope is? Whether you know the telescope moves, especially if the telescope is not on the North Pole, it moves. So how do you know the position of the telescope? So in fact, what they did for the observation of exactly this photo is not just 2 telescopes, but 8 telescopes. So there were 2 in Chile, 1 in Spain, 2 in Hawaii, Mexico, USA, Antarctica. So I've drawn them roughly on the globe here, and there wasn't any on the North Pole, okay? I kind of cheated. And especially when you hear the Earth spins, so you really need to know the position of your telescope. What you can do is you look at the same time at an object which you know very well in sky, another star, and from this you measure your rotation. In fact, this is exactly the way we measure the fact that the spinning of the Earth isn't stable, what you said. This is what my colleagues did at observatory. I wanted to put in a picture, but I thought it's too complicated. So you're too good. So they used 8 telescopes, and the resolution of looking at this image of the whole combination of data is as reading a newspaper in New York from Paris. So you look across the Atlantic and you read the newspaper. It's kind of difficult because the Earth is a sphere. You can't look to New York, but you can imagine. Okay, that's a summary of my second part. A distance object can only be observed by combining distant telescopes. Atomic clocks grant a correct combination, and telescopes all over the world were used to observe this black hole at the center of the galaxy, Messier 87. How are you? Fine? Okay, I have 3 more slides as a, yes, please. So you can, you observe the sky anyway in any direction. You can predict that there is the center of the galaxy. It's like looking out in the sky, you see the Milky Way, you know this is the center of our galaxy. So you know this is the center of the galaxy, you have to look in this area. Then by seeing the number of the stars in the galaxy, and the movement of the stars in the galaxy, you can guess there's something very heavy in the center of the galaxy. So this may be a black hole. Basically, you look in any direction which is possible, and if you're lucky, you see one. It's like making the film which we saw early on. You take 5 years looking at the boys, and once you're lucky, you see them coming out of the door. Okay, if you give me 5 more minutes, I tell you what is a black hole. Do you want to know this? Yes. So as you gave me 5 minutes, I can show a second formula. You still know Albert Einstein, and you might have seen this formula, E equals mc squared. Who has seen this formula? No. More of you have seen this formula. Yes, okay. So it's really the formula you saw, okay? It's not something different. So the E stands for energy, the M stands for mass, and C is the constant, it's the speed of light, okay? And the 2 is obviously c squared. Energy in this case is light. Light is energy, photons are energy. So the formula says that light has mass. It weighs something. If I have light here, which is actually the one going on the screen, it goes like this. It falls down because light has mass. So light is attracted by gravity, which can be our Earth, and it falls down like everything falls down. Only on the projector you don't see it fall down, you don't see the image here. It's because it's going so fast that it doesn't have the time to fall down, okay? But if I have a very massive object, which is a black hole, the attraction of the light of this massive object is so strong that the light will fall into the massive object. And the theory I present to you now was developed by Karl Schwarzschild, the 3rd German physicist in my talk, who also lived at the turning of the 19th, 20th century. So this was a very important period for modern physics. So it depends on how far the photon started from the center of the black hole. If it's near enough, the center line here, it will fall into the black hole. If it's further apart, it will be attracted, but it can escape. It's because the attractive force is limited. We are on the ground, we stay on the ground because we're attractive. But if you go into space, then you may escape because you're too far from Earth, and you float into space. This was the subject of the film Gravity with Halle Berry. So it depends on where the photon comes in, whether it gets sucked in or whether it can escape, and that's how exactly this image occurs. Photons which are far enough away, they can escape, they come to our telescope, to our eyes, and the photons which are too near to the center, they stay, they get sucked in, so it's black. This is really the end. Thank you very much. So do you have any other questions? Yes. The usefulness of observing black holes. I guess it's to understand, again, how the universe forms and why the stars evolve around this object the way they do. Energy? Say more about energy or light. Yes, the question is, can you say more about energy or light or black holes? It's like starting my talk.
We can stay till tonight.
I can tell you a different way of observing black holes is you look at the stars which evolve around, and you can measure their trajectory by looking at them like in a film. And from this trajectory, you can calculate how massive the object is in the center. So you can say whether it's a black hole or just another massive star and so on. Yeah. Yes, in the back. Yes, they are empty inside, and that's why they are black inside. Here. And the radio waves, they come from the outside. So whether we talk about light or radio waves is the same thing. Okay. It's only that radio waves we can't see with our eye. Okay. There were more questions here. Yes. In our galaxy, as far as I know, there's no black hole. No. But which doesn't mean that one day our galaxy will be attracted by a black hole. Yeah. It crashed. The question is whether from these works I have an idea when Jesus will come back. So there, maybe we can ask the question differently, is we know that the universe came from the Big Bang. The one question is, will it collapse again to give another Big Bang? Because many black holes, they will all attract each other. And this was a very discussed question, and as far as I know, the stage now is that it will continue to expand. It will not collapse. Yeah. There's a second question. Yes, please. So the question is, first of all, we're collaborating with other countries, and second, how much does this cost? What's the budget? So the answer to the first question is that for the moment, each country is responsible for its own time. So you have an institute like us in France, in Germany, in England, in Italy, in the US, and so on. There are smaller countries which, of course, can't afford a laboratory like ours, so they rely, for example, on GPS time and so on, or they buy commercial clocks. So the budget for this what's the good measure? I would say to build a clock like the one you saw is about €1 million salary and material. But this is over 20 years. So on a yearly basis, it's not very much. So which is 50,000 a year. Oh, no, that's too small. let's say 5 million euros. Yes, please. So the color on this image is artificial. It's you would see light and gray, but it's nicer if it's yellow and white. Sells better. Please, yes, you were. So, yes. As far as I know, so this is not my speciality. Huh? As far as I know, matter just stays in there and becomes a big lump, I don't know, or even denser than a big lump of material. I don't think it will become a new star or something like this, because everything is just attracted into the center. Yeah. Please. The universe. Yes. No, not the black hole, the universe. Yes.
But is this potential black hole been measured?
This one, I don't think so, since the observation is quite recent, but I can imagine they're continuing to look at it and trying to measure whether it gets bigger. Yes. Yeah, please.
How many atomic clocks develop in the world?
Please repeat. How many?
How many atomic clocks develop?
How many atomic clocks in the world? So it depends on how good the clock really is. I always talk about identical clocks, but they are never identical, as I showed to you. So you can buy atomic clocks which are at 10 to the minus 12. Okay? I don't remember. So I told you 10 to the minus 18. 10 to the minus 12 is 1,000,000 times less good. This is what you can buy, but they produce, I don't know, 50 a year or 100 a year. This is, the laboratory clock which I worked on, there are about 10 in the world. And these are the clocks which really make time today.
Last question.
In this case, the light comes from a material which is attracted towards the black hole.
Which is heated and then...
It goes so fast, it is heated, that it starts to glow. So the right time is not one clock, is an average of the 10 clocks. So you send in, again, numbers. The BIPM calculates the average and gives the right time. The average is, so the better your clock, the more weight it has in this average. So there were times when my clock was the only, or one of three, I don't think, good clocks which contributed, so it had a big weight. Now that you have 10 clocks, the weight is smaller. The weight depends on the accuracy we give, we work out, but it also depends on how long the clock has worked continuously. So the BIPM, obviously, they want to keep it very good. It's like the church. We want to have a good stability in time. So we don't jump on the newest occasion. We don't jump on the newest clock. We say, well, this clock has to run for, I don't remember, 3 or 4 or 6 months before we take it into the average. Very conservative, of course.
Good. I think we'll stop here because we're hungry. No, because we have the program.